Okay, welcome to EGR445. And in today's class, I'm gonna continue the discussion that we started in last class. We were talking about torsion and bending. So, torsion leads to shear stresses and bending leads to normal stresses. What we will do is we will work out the problem of torsion, we will work out the problem of bending independently, and then we will look at a case when both these moments, twisting moment and bending moment, they act simultaneously. So a quick recap: the fundamental equation for torsion is T divided by J is equal to tau divided by R is equal to G theta divided by L. And we defined the terms of this equation. For bending, it is M divided by I is equal to F divided by Y is equal to E divided by R. Please note the structure of these equations is same. In the case of torsion, we have J, that is polar moment of inertia. In the case of bending, we just have moment of inertia, which is nothing but the second moment of area. So I'm going to work out problems with pure torsion. The problems with pure torsion include the problems wherein the shaft is transmitting power, or if you have couplings. So shaft and couplings are designed on the basis of torsion equation. So let me take a problem. So a shaft is transmitting, this is P, which is the power transmitted by shaft, which is 100 kilowatts at speed n is equal to 160 RPM. Now we have to find out the diameter of the shaft. Find the diameter of the shaft, assuming starting torque is 25% of nominal torque. So power is given to us, speed is given to us, but there is a condition that the starting torque is 25% of the nominal torque. The material is steel and tau design is equal to 70 megapascal. And in last class, we looked at 70 megapascals is 70 Newton per millimeter square. So now we will start with the very first equation. P is equal to 2 pi n t divided by 60, where P is the power in watts, which is 100 kilowatts, is equal to 2 times pi, speed is 160 times t divided by 60. So once you solve this equation, you should be able to tell me the value of the torque. And the value of the torque, T, my answer is 5970 Newton meter. Please note, this is a large torque. This is the torque that is applied in steady state. So this is the nominal torque or the mean torque. So what is this starting torque? If you think about it, usually the shaft is between an engine. So this is an engine. And then there is a pump. So for an example, say you have a pump. And then there is a shaft between the engine and the pump. Now, if you think about this load, I'm going to call this pump. Initially, everything is stationary, which means the bearings, they are not rotating, the water is not churning. So initially, just to start, there is a spike in the torque requirement. And the reason for that is the static coefficient of friction for different components is greater than the kinematic coefficient of friction. And sometimes the starting torque exceeds the nominal torque. However, we want our shaft, which is between engine and load or pump, to sustain not only the nominal torque, but also the starting torque. So if we want to design the shaft, if we want to find out the diameter of the shaft, then we need to make sure that this shaft is able to support the maximum torque that engine is going to supply to the pump. So T max is equal to 1.25 times 5970 Newton meter. So this is the maximum torque that will be supplied by the engine. Now for the shaft design, we are going to use the equation T divided by J is equal to tau divided by R. Now in this problem, they don't mention whether it's a solid shaft or it's a hollow shaft. For an example, if it's a solid shaft, it is something like this, and this is the diameter D. And value of J in the case of solid shaft is pi d to the power 4 divided by 32. Sometimes they ask you, or if the problem says that we have to design a hollow shaft, in the case of hollow shafts, you have an outside diameter and an inside diameter. So you will have a D outside and you will have a D inside. D inside. So J is equal to pi by 32 D outside to the power 4 minus D inside to the power 4. Now I just want to clarify the difference between the shaft and a pipe. And again, pipe also has an outer radius and the inner radius, or outer diameter and inner diameter. But in the case of pipe, the thickness, which is this, is very small. In the case of shafts, this thickness is non-trivial. So most of the times, what they do is they provide a ratio between D outside and D inside. So they could provide a ratio, and we have to use this ratiometric relationship. Say ratio is 1.25. We have to use this ratiometric relationship to find out the value of J. In this problem, for simplicity, I'm going to assume the shaft is solid. And when the shaft is solid, using the equation 1.25 times 10 to the power 3, 5970. And the reason for this is so that the unit here are Newton millimeter. And the reason for that is the stress value is in Newton millimeter. The value of J is pi by 32 d to the power 4 is equal to tau value, it's 70 divided by r, which is the radius, which is d by 2. And now the only unknown in this equation is the value of d. And I want you to look at this calculation, and my answer is 83 millimeter. So the shaft diameter is 83 millimeters. Any question on this problem? Now, the next problem that I want to look at is bending. So similar problem, but now we have a circular rod, and we have to find out the value of the bending moment, and then we have to find out the diameter. So let's look at the next problem. So consider the shaft assembly shown in figure. Now what we have in this figure is, this is the shaft, this shaft is supported at the end. So here there are bearings. So this is where the shaft is supported. And there are two pulleys. So there is one pulley over here, and there is one pulley over here. There are two pulleys, and the weight of the pulley is 25 kilonewton. That is the weight of the left pulley. And you have the right pulley. The weight of this right pulley is 35 kilonewton. Now, the locations of the pulleys are given as, this distance is 150, this distance is 200, and the distance between the pulleys is 600. So I'm gonna call this support A, I'm gonna call this support B. And they are asking, find diameter of shaft, assuming sigma bending design is equal to 100 Newton per millimeter square. So now in this problem, what we have is we have a shaft, but this shaft for the time being is not rotating. So please note, there is no torque. This is an important observation. So no torque. So there is no torque. So right now, this shaft is doing nothing but supporting the load or the weight of the pulley. So this is actually a bending problem. So if I were to draw the free body diagram, or if I were to draw the, the schematic or the layout, I'm gonna see a reaction on the left hand side. I'm gonna see a reaction on the right hand side. There is going to be a downward load 25 kilonewton. There is going to be a downward load 25 kilonewton. So sorry, this is 35 kilonewton. Downward load 35 kilonewton. And this is how the loading diagram will look like. Now what I need to do is, based on this loading and these dimensions, let me write these dimensions down. This is 150, this is 600, this is 200. Based on these dimensions, I need to find out the reactions RA and RP. So taking moments about B. So taking moments about B. Taking moments about B, I find 35 times 200 plus 25 times 800 divided by the total distance is 950. That gives me RA. So RA, I can find out the value of RA. Just use your calculator and find this value. My answer is 28.42 kilonewton. So the value of RA is 28.42 kilonewton. RB is equal to the total load 25 plus 35 minus 28.42, which is 31.58 kilonewton. So I have these two reactions, 28.42 and 31.58. Now I need to find out the maximum bending moment. Now, how do I find out where the maximum bending moment is? So I'm sure you studied in mechanics of materials, or EGR343 and EGR444, that the bending moment is maximum where the shear force changes the direction or changes sign. So when shear force goes from positive to negative, that is the point where the bending moment is maximum, because derivative of bending moment is shear force. So how do you draw a shear force diagram? For this problem, I just want to show you the technique that I use to draw the shear force diagram. You will go from left to right, and always remember this. Go from left to right and then follow the arrows. So for an example, you have an array. This array is 28.42. So 28.4. Then continue straight, straight, straight. Now you see this another arrow of 25 that is going down. So what you will do is you will go down by 25 and then again go straight, 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 straight. And then here you see another arrow of 35 pointing towards downwards. So you go down, then there is nothing else, go straight and then go up. So that is how the shear force diagram is gonna look like. And you can use this technique to draw the shear force diagrams in the cases when the load is changing, or you have a uniformly distributed load, you have a uniformly varying load, or you have a complicated loading condition. Always go from left to right because that maintains the sign convention, and follow the arrows. So if the arrow is pointing go up, you go up. If the arrow is pointing downwards, you go down. Now in EGR 343 and perhaps in EGR 444, you might have drawn the bending moment diagram for the entire shaft. But please note, we are only interested in finding out the maximum bending moment because this is a design problem. We want to find out the diameter of the shaft that can withstand the maximum bending moment. Please note, this is the location where the bending moment is going to be maximum. So this is the location where the bending moment is going to be maximum. So I'm going to call this point C. So I need to find out the bending moment at point C. And this bending moment can be found out either considering the moment of forces on the left of C or the moment of forces on the right of C. So quick recap, if you want to find out the bending moment at C, what you do is you consider this section XX. And what you can do is you can find the sum of the moments of the forces that are on the left of C, or you can find the sum of the moment of the forces that are on the right of C. Now, if you look at on the left of C, there are two forces. So you have force number 1 here, and then you have force number 2. On the other hand, on the right of C, there is just one force. So it's just easier to take the moment of the forces that are on the right of C. And if you look at the moment, here is another convention, all upward forces. So upward forces, they give positive bending moment. So if you look at RB is going up. So that upward force is going to give you a sagging curvature. That means it will give you a positive bending moment. So that bending moment is going to be 31.58 multiplied by 200. Please note, the force unit is kilonewton, the distance unit is millimeter. So your bending moment, the maximum bending moment is 31.58 multiplied by 200 kilonewton millimeter. So the bending moment is 6.32 multiplied by 10 to the power 6 Newton millimeter. Now what I'm going to do is I'm going to use this bending moment in the bending equation. The bending equation is the fundamental equation of bending. M divided by I is equal to F or sigma divided by Y. M is the bending moment, which is 6.32 10 to the power 6. Now value of I, this is important. Please note this is a circular cross section and we are going to assume a solid circular cross section. The value of I for circular cross section is pi by 64 times d to the power 4. If this would have been a hollow shaft, so if this would have been a hollow shaft with d outside and d inside, then I is equal to pi by 64 d outside to the power 4 d inside to the power 4. Now this is a solid shaft, so I'm going to use the equation pi by 64 d to the power 4. Now the maximum stress value is 100 Newton per millimeter square. So I'm going to write 100 and value of Y is d by 2. So the only unknown in this entire equation is d, and my answer for d is 90 millimeters. And please note, I'm rounding off on the higher side. So if you get answer 88.5 or 88.9, I would just round it to 90 millimeter because this is a standard shaft size. So this is the standard shaft size. And once again, in design, the purpose is that design should be safe. But a word of caution, it should not be overly safe, which means if the diameter of the shaft 90 millimeter is sufficient, you shouldn't use a 200 or 300 millimeter diameter shaft because that would be an overkill. So, but if the dimensions are 85, 87, 88, 89, and then the standard shaft size that is available on MacMaster or in the machinery's handbook or design data book is 90 millimeter, then you can actually pick up that shaft dimension. Now, the next question is what happens? So here is the next question. What happens when bending and torsion act simultaneously? So we briefly discussed this question in last class. You have the bending moment that gives rise to the normal stresses. You have twisting moment that gives rise to shear stresses. If you look at an element, the normal stresses, they are perpendicular to the area and the shear forces are parallel to the area. So you have a combined loading state. So you have sigma n and tau acting simultaneously. So when you have these two forces, when these two stresses acting simultaneously, we have the concept of principal stress. Now, as you know from EGR343 and EGR444, there are two principal stresses. One is a maximum principal stress, and the second one is the minimum principal stress. Now, in the design problem, we just want to make sure that our shaft is able to sustain the maximum principal stress. So the maximum principal stress, and I'm going to call this sigma max, is given by the equation 1/2 sigma plus square root of sigma square plus 4 tau square. So this sigma is nothing but sigma n. So this equation is given as sigma n plus sigma n square plus 4 tau square. Now let's look at what this equation means, and let's try to understand the physical understanding of this equation. When you have two stresses acting simultaneously, these two stresses give rise to a resultant stress. Principal stress is the projection of that resultant stress in the normal direction. So principal stress is sometimes also called as equivalent normal stress acting due to combined action of of sigma n and tau. Now a thought exercise: in the principal stress equation that I have shown over here, assume tau is equal to 0. So this tau, assume it to be 0. And you will realize for tau is equal to 0, sigma max is nothing but sigma n. So what it means is when there is no shear stress, principal stress is nothing but the normal stress. And I will explain this concept once again. So look at the way the stresses are acting. Tau and sigma n, they are perpendicular to each other. So because tau is acting parallel to area and sigma n is acting perpendicular to area. So what happens is when these two stresses, they act together, and probably you studied that by drawing Morse circle. So when these two forces act together, they give rise to a resultant stress. Now that resultant stress, basically, if you resolve it along perpendicular to the area, that is nothing but the principal stress. And if you resolve that stress along parallel to the area, which means in the shear stress direction, that is nothing but maximum shear stress. So maximum shear stress is nothing but tau max is equal to 1/2 square root of sigma n square plus 4 tau square. So this is the shear stress, or I would call this equivalent shear stress acting due to combined action of sigma n and tau. Now again, you can perform the same thought exercise. So if you assume in this equation sigma n is equal to 0, then you will see tau max is equal to tau, which means when there is no normal stress, the maximum shear stress is the shear stress itself. And remember this interpretation because this is very, very useful. Now, the question that may arise is what about the minimum shear stress, or what about the uh, minimum principal stress? Those stresses are important and they do exist, but in the case of design, we want the design to be safe. Safe means the design should be able to withstand the maximum principal stress and maximum shear stress. So what we want to do is, when we design, we want to make sure that the maximum principal stress and maximum shear stress conditions are met. Our shaft is strong so that it can withstand these two stresses. So how do we design shafts when we have these two stresses simultaneously acting? And there are two techniques. I'm going to show you the technique that you probably learned in the case of mechanics of materials 343, and I would give you a sort of a simpler method or sort of a shortcut technique to work out the problem. So let me set up the problem. Consider that this is the shaft design under combined loading. So shaft design under bending and torsion. And the problem is something like this. So here is this shaft, and this shaft is supported in the bearings, and this shaft is supposed to transmit the torque T. This is the torque that is transmitted. And on this shaft, there are different loads. So there is a load P1 and there is a load P2. Now these loads could be because of the pulleys, so or they could be because of the gears, or they could be because of some other elements, the machine elements that are on the shaft. So what we need to do is, first and foremost, we need to find out the reactions. So I'm going to call this RA and I'm going to call this RB. So step one is find reactions. The reactions are RA and RB. And you would use the conditions for static equilibrium to find the reactions RA and RB. The next step is draw bending moment diagram. And when I'm saying draw bending moment diagram, the sole purpose of this bending moment diagram is to get maximum bending moment. So if you are comfortable in shear force and bending moment diagrams, you sometimes don't even need to draw the bending moment diagram to find the maximum bending moment. You can see where the shear force is changing the direction and find the bending moment at that location itself. So the idea is we will get the bending moment. Next step, so we have bending moment, and I'm going to call this M. So M is the maximum bending moment. And then I'm going to say T is the torque. At this stage, there are two ways to solve this problem. So there are two ways. And both of these will give you the exact same answer. So what we do is, first and foremost, from the bending moment, we find out the bending stress. So the equations that we use is M divided by I multiplied by Y, M divided by I multiplied by Y. That gives me sigma N. The second equation is using the torque equation, T divided by J multiplied by R gives me value of torque. The next step is, from bending stress and the shear stress, I find out the maximum shear stress, which is tau max, is equal to 1/2 sigma n square plus 4 tau square. And I need to make sure that is less than tau design. I can also find out maximum principal stress, which is sigma max, which is 1/2 tau n plus square root of tau n square plus 4 tau square. And this has to be lower than sigma design. This is one process in which you can solve this problem. But now I just want to outline some of these issues. This process is perfectly fine when the shaft dimension is given and you have to find out the principal stress. So assuming D is known, and you have to find out sigma max, tau max, and sigma max, this process works very well. And that's what you have used in EGR443. However, in the design problem, what we want to do is we want to go from tau design to the diameter of the shaft, or sigma design to the diameter of the shaft. And out of these, you would choose the max dia. Now here, the problem becomes slightly complex. And I want you to understand why the problem becomes complex. Because please note, in this equation, this is expressed in terms of diameter. So this is expressed in terms of diameter. In this expression, this is expressed in terms of diameter. And depending upon whether you have a solid shaft or a hollow shaft, you are gonna get an equation that could involve inside diameter and outside diameter. Now realize here, now you will have an equation which will be a quadratic equation in terms of D. Here, you are gonna have a quadratic equation with a linear term in terms of D. And this equation tends to become little complex when you have hollow shaft. So there is an alternate way the problem can be solved. And usually I would prefer the second way of solving the problem. So let's look at where we are. We are looking at the shaft design problem under bending and torsion. The loading is given to us, the torque value is given to us. And we set up the problem and we found out the reaction RA and RB. We got the maximum bending moment either from by the shear force or we found the bending moment diagram and then found out the maximum bending moment. So now we have the maximum bending moment and we also have the torque. So what we can do in the alternate process is we will find out the equivalent torque or the resultant torque. Now please note, diameter does not appear in this equation. Resultant torque is simply given by equation m square plus t square. So this gives me a resultant torque. And what I do is I find out the diameter using this resultant torque equation. So basically, I will say tau design. Please note this tau design is equal to TEQ divided by J times R, where J is, say, if it's a hollow shaft or if it's a solid shaft, pi by 32 d to the power 4 and R is equal to d by 2. So from here, from this equation, I should be able to get directly the value of D. Now, if I want to find out the M equivalent, EQ, that is given as 1/2 M plus square root of M square plus T square. And then what I do is I say sigma design is equal to MEQ divided by I multiplied by Y, where I is equal to pi by 64 times d to the power 4 and Y is equal to d by 2. Now I want you to take a moment and look at the similarities and differences between the techniques that we have over here. And if you really want to get into the details of this technique, you can prove the equivalence very easily. For example, you can substitute the you can find out the value of sigma n and tau in terms of m and I, and then you can actually factor out the terms and you will see that these equations, so basically they have one-to-one correspondence. So I will just tell you what this means. So this equation and this equation, it is the same. This equation and this equation is the same. So you can use any of these techniques, you will get the same answer, but my choice would be this. This would be my choice because we would use this technique when we are going to design the shafts for the gears. When we look at the shaft design in gear, we don't use the principal stress and tau max technique. We go with the equivalent torques and equivalent moment technique. So might as well stick to a consistent equation. Yes, in this problem, either the torque is given or alternatively power in kilowatt. power in kilowatt, and speed in RPM is given. So torque is known. So what I'm going to do now is I'm going to work out a problem when you have this combined uh, loading, which means you have the torsional moment and you have the bending moment. Before I proceed, I just want to ask if does anyone have any question? If you have any questions, please go ahead and raise your hand and I can unmute you, or you can ask questions via chat. Okay, since there are no questions, I will go ahead and work out a problem. So consider the shaft shown in the figure. So next problem, consider shaft shown in figure. And if you look at this shaft has different types of loading. So what it has the bending load, it has the shear load, and we have to find out the total stress. So this shaft is like this. It is supported at the end, and there is a pulley at the center. So there is this pulley. This distance, actually it's not at center, it's slightly offsetted. So this distance is 300. This distance is 600. And the power transmission is 5 kilowatts, and the speed is 200 RPM. So this is a little tricky problem in a sense that the weight of the pulley is equal to weight of the pulley is given as they give you the weight of the pulley. Yeah, the weight of the pulley is given as W power transmission, the tension ratio is equal to 2.5 and the weight is 400 Newton. And the diameter of the pulley, is equal to 270 millimeter. So this problem is a little tricky. So we will go, we solve this problem step by step. So first and foremost, what we have is, we have this shaft that is transmitting 5 kilowatts at 200 RPM. So 5 kilowatts at 200 RPM. And what I want you to do is, I want you to look at the side view of this pulley. And I'm going to draw the side view of this pulley. If you look at the side view of this pulley, the diameter of the pulley is given to us, which is 270 millimeters. 270 millimeters. Now, clearly, this is a belt drive, which means what you have is, you have a belt that is around the pulley. So if you can think about it like this is a belt, and this belt is attached to maybe some sort of a generator. So what you have is, you have the shaft, you have this pulley, and there is a belt. Imagine this is the similar type of belt that you have in your cars, and that belt is driving a generator. So this is driving a generator. Now what it means is, if you look at the power flow, and this is very important, if you look at the power flow, 5 kilowatts of power comes to the shaft. So probably the shaft is attached to some engine. So there is an engine somewhere over here. So there is an engine over here. This is engine. And the 5 kilowatts of power at 200 RPM is transmitted to the pulley, and this pulley is attached to another pulley through a belt drive. So there is a belt drive, and this belt drive is driving this generator. And this is quite large pulley. 270 millimeter is a quite large pulley. So the weight of the pulley is 400 Newton, which is approximately 400 kilograms. So you have a 400 Newton pulley. Now, how do these pulleys transmit power? And I just want to give you a brief understanding of power transmission in pulleys. And I want you to look at this power transmission diagram. So consider that there is a pulley here, and there is another pulley over here, and there is a flat belt. So this is very important. There is a flat belt. So clearly there is a driving pulley. So I'm going to call this a driving pulley. And this is the driven pulley. So you would observe that this pulley, and this is the belt. So there is a belt here. This is the belt. And I'm going to assume that this is flat belt. So this is not a V belt, or this is not a serpentine belt or timing belt. it just is a flat belt. So what happens is, as this pulley is rotating in the clockwise direction, the belt here will be stretched. So please notice the belt here will be sort of stretched. And belt here will be sort of compressed or pushed. And I want you to visualize what is happening. If you look at an element of belt, so let's try to trace an element of belt over here. This belt element, as it travels over the pulley, this element here is stretched. In other words, if I were to draw the free body diagram, and now this is important. So if I were to draw the free body diagram of belt, you would observe the belt here is stretched. And you would observe the belt here is sort of little bit pushed, but still it is stretched. So you're gonna have belt which is something like this. So this is how the power transmission is gonna look like. Because please understand, it's a belt. Belt cannot transmit power in compression. Belt has to be under tension all the time to transmit power. So, but the tension on the top side, this is also called as the slack side. Since the element is sort of pushed, so this is called as the slack side. And this is the stretch side. So this is slack, this is stretch. You're gonna have different tensions, T1 and T2, on the two sides of belt. So you're gonna have T1 and T2. These are two different tensions on the side of the belt. And that is called as the tension ratio. So T1 is also called as the tight side tension, and T2 is called slack side tension. And T1 divided by T2, this is called as the tension ratio. And if we get chance, we will study the power transmission and design of belt drives. But I want you to remember this equation just in case. This is given by E to the mu theta, where mu is the coefficient of friction between the belt and the pulley, between belt and pulley. And theta is angle of overlap. So in other words, this is angle theta. And so depending upon the value of mu and the value of theta, you will get different values of tension ratios. But in this problem, the good news is the tension ratio is directly given as 2.5. So the tension ratio is given to us. The equation for power transmission in the case of the belt drive is T is equal to T1 minus T2 multiplied by R pulley. So please note the torque transmitted by pulley, which is the torque transmitted by pulley, is difference between the tension on the tight side and the slack side multiplied by the radius of pulley. And I just want you to think about this a little bit. When you are biking and when you are actually pedaling, you will observe that on the chain you have a tight side and you have a slack side, and that is because the chain also transmits the power using similar principles. Just like the belt drive, you have to find out the tensions on the tight and slack side, and that gives you the power transmission relationship for even for the chain drive. But I want you to understand the equation here, and I will write this down. Torque transmitted by belt drive, which is equal to T, that is given as T1 minus T2 multiplied by R pulley. Now, why all these equations are important? So let's start with the setup that we have. We have a shaft, and on this shaft we have a pulley. This pulley itself has some self weight. So this pulley has a self weight W. In addition to this W, this belt is applying some tension T1 here and some tension T2 over here. So in other words, if you look at the load on this shaft, the total load on this shaft is going to be the weight of the pulley, tension on the tight side, and the tension on the slack side. So we have to find out the, the torque transmitted, we have to find out the loads, and then we have to find out the bending moment, and then we have to find out the torque. So this is how we will go. So we'll start with step 1. So power is equal to 2 pi nt divided by 60. Now the power is given as 5 kilowatts, which is equal to 2 times pi. Speed is 200 times t divided by 60. So when we solve this, we will find out the value of torque, and my answer here is 238.73 Newton millimeter. Please use your calculators and tell me if this answer is correct. So the value of the torque is 238.73. If you look at the power transmission by pulley, a power or torque transmission by pulley, that is T is equal to T1 minus T2 multiplied by R pulley. So T is given as 238.7. T1 by T2, T1 by T2 is equal to 2.5. So that gives me T1 is equal to 2.5 times T2. So 2.5 times T2 minus T2 multiplied by R pulley. Please note the diameter of the pulley is given to us. So the radius of pulley is diameter divided by 2. So from this equation, I should be able to find out the value of T2. And the value of T2 is 1178 Newton. And then the value of T1 is 2.5 times T2. That gives me 2947 Newton. So I have these two values of tensions. So let's look at the loading on the shaft. So I have this shaft, and this shaft is supported at the end. There is this pulley at the center, and at this pulley there are three loads. There is W, which is the weight of the pulley, plus there is T1, which is tension 1, tension on the tight side, and tension on the slack side. This is the total load at the pulley. So this total load should be used to find out the bending moment. So this total load, I'm going to give you the answer, which is 400 plus 2947 plus 1178. This is the total load at the pulley, and this distance is 300. This distance is 600. So I can find out the value of RA, and I can find out the value of RB. So for an example, RB is equal to W plus T1 plus T2 multiplied by 300 divided by 900, and RA is equal to W plus T1 plus T2 minus RB. And clearly, if you draw the shear force diagram, I'm just going to draw shear force diagram over here. The shear force diagram looks something like this. So this is A, this is B, and this is C. So at C, the shear force is changing the direction, which means the bending moment is going to be maximum at point C. So what you can do is you can find out the maximum bending moment, Bm max, is equal to Ra multiplied by 300 Newton millimeter. And what I'm going to do is my answer for the bending moment maximum, my maximum bending moment, I will give you the value Bm max is equal to 905.2 10 to the power 3 Newton millimeter. This is the maximum bending moment. Now I'm going to follow the procedure which is shown on the left hand side. So what I will do is I will find out the T equivalent. T equivalent is T square plus bending moment maximum square, and my answer is 936.18 10 to the power 3 Newton millimeter. Because please note, value of torque is known. We know the value of torque. We know the value of the bending moment. So I can use the relationship for T equivalent and find out the value of T equivalent. And tau is equal to T equivalent divided by J multiplied by R. And here I'm going to assume steel shaft. I'm going to assume steel shaft, and you will have to look at the design data book to find out the value of tau design for steel shaft. Tau design, that is 40 Newton per millimeter square. It's always safe to assume tau is equal to 40 Newton per millimeter square. That gives you about factor of safety of 4. So tau design is 40 Newton per millimeter square. So 40 is equal to 936.18 times 10 to the power 3 pi by 32 d to the power 4 times d by 2. And that gives me the value of d is equal to 50 millimeters. And this is the shaft diameter from T equivalent, alternatively tau max criteria. Next thing is I can find out the M equivalent, which is given as 1/2 M plus square root of M square plus T square, and that equation is 1/2. We know the value of M, which is 905 10 to the power 3 plus square root of 905 10 to the power 3 square plus 238.73 238.73 square. And what we can do is we can find out sigma design is equal to MEQ divided by I multiplied by Y, where value of I is pi by 64 t to the power 4 and y is equal to d by 2. So when you substitute these in this equation, and for steel, sigma design for steel, sigma design is 80. You can use anywhere between 60 and 80. So I'm just to be on conservative side, I'm going to use 60 Newton per millimeter square. So this is equal to 60. You can find out the value of D is equal to 55 millimeter. So please note, now we have two values. One is diameter of 50 and diameter of 55. And always choose the largest value. So this is going to be our shaft diameter. So if you look at the procedure, what we did, we had a shaft that is subjected to bending loads. Then we found out the reactions, we found out the maximum bending moment, we found out the equivalent torque and equivalent moment, and then found out the diameter. And we used the maximum diameter. So when we look at the gear designs and even internal combustion engine design, connecting rod, crankshaft design, we will use the exact same process. Okay, 7:20, I'm gonna give you all a 15-minute break and we will continue, we'll start our first topic, which is the design of quarter joints after the break. Okay, so in this session, we are going to talk about design of quarter joints. So design of quarter joint. Now, what is a quarter joint? So quarter joint is used to connect rods. Now, I want to give you a very simple example. Imagine that you have a steam engine. So this is a steam engine. And this could be a single acting or double acting steam engine, which means it could have valves on both the sides. And again, you will have a steam generator, like a boiler. And then this can go to a condenser. And you have these valves, V1 and V2. They open and close sequentially so that the hot steam can enter on one side and then maybe exit on the other side. So depending upon the design of the steam engine, you could have a single acting, which means the steam goes only from one side and exhaust from other side. Or you could have a double acting where the steam engine or the steam can go from the piston side. This is called as the piston side, and this is called as the rod side. So you can have hot steam uh, doing work from the piston side as well as on the rod side. Now, what happens is this piston is connected to a connecting rod. So this is called as connecting rod. And this connecting rod is usually connected to some sort of a slider crank mechanism, wherein this crank rotates. So the purpose, this is called as the crank. So the purpose of this mechanism is to convert the reciprocating motion of the piston into the rotary motion of the crank. So reciprocating motion of piston is converted to rotary motion. And this rod could be made up in sections. So for an example, you could just have one rod connected over here, and then you have the second part of the assembly, which is over here. Now, what needs to happen is you need to make a connection here. So I'm going to call this point A. So there is a rigid connection at point A. So this connection is connecting rods on the left-hand side and rod on the right-hand side so that the reciprocating motion is transferred. And how does this system or this assembly work? So usually what you have to transmit the reciprocating motion, so to connect rods, so you have something called as the quarter joint. Now I'm going to draw a three-dimensional view of the quarter joint. And actually the principle of a quarter joint is very simple. And in the last class, we kind of talked about the assembly. So this is how the quarter joint looks like. So what you have is you have a spigot end. So you have a spigot end, and then you have a socket end. So if you look at, so what you have is you have a socket end, something like this. So this is called as the spigot. This is called as the socket. And this side, you can think is connected to the piston, and this side is connected to the crank assembly. So the idea is that the spigot and socket together, they connect and they allow reciprocating motion to transmit. Now, there is a cotter. So what we do is, if you look at the way the cotter is, the, the spigot goes inside the socket, and then what we do is we hammer a cotter in. So there is this cotter. So this is called as cotter. So the idea is you insert the spigot into socket, and once you insert it, what happens is this is called as the socket collar. This socket collar rests against the spigot collar. So this is the socket collar. Socket collar. And this socket collar rests against spigot collar. And when they are aligned, these holes, the spigot hole, and I'm denoting this as S, and then the socket hole, which is SS, they align. And once they are aligned, basically you insert this cotter, and this cotter is hammered in so that it tightly fits between the socket and the spigot. So in other words, when the piston is reciprocating, going forward and backward, the spigot along with cotter, along with socket, they transmit this reciprocating motion. Now the key question is, how do we design this cotter joint? And the fundamental design principles of cotter joint are nothing but force divided by area is equal to stress. So if you look at the different cross sections of the socket joint, what we will do is we will look at the failures of the cotter joint, and then we will identify different areas. So what we are going to do is we are going to start uh, from left hand side. And before I start, I just want to tell you that this is the dimension D. This dimension is same as this dimension D. This dimension will be determined first. Then we will look at the failure of socket, spigot. Then we will look at the failure of cotter. Then we will look at the failure of socket. And then we will identify, we will find main engineering dimension. Find important engineering dimensions. However, a word of caution. The calculations that we are going to do will not determine all the dimensions. Some of these dimensions are from the geometry point of view. In other words, we are going to look at the dimensions that are critical for the cotter joint to function. But based on those critical dimensions, there are some associated dimensions that are required to actually draw or to build the cotter joint. And those dimensions, they come from empirical data. So what we will do is we'll find out the important engineering dimensions. Then we will use the design data book to find out the other dimensions of the cotter joint. And there is another variation possible, which is called as the double cotter joint. So in class, I will discuss the single cotter joint. Principle of double cotter joint design is exactly same, and you can look at the worked out example in the textbook that talks about design of double cotter joint. So whenever we design the cotter joint, here is the information that is given to us. So they will give you the load that is to be transmitted. So the value of load will be given. Then the material will be given. So based on the material, you can find out the values of sigma, values of tau from either the design data book, or machinery's handbook. If you look at the textbook, in the appendix, they have given important engineering engineering properties of different materials. There's an entire chapter, I think it's chapter 2, devoted to engineering materials. But the idea is you look at the design data book and then get these values. So I'm going to give you a sort of a step-by-step procedure on how to design the cotter joint. And then what you can do is you can follow that step-by-step recipe to actually design the cotter joint. Once you find these important dimensions of the cotter joint, once these important dimensions are found out, what you can do is you can actually start drawing. So first step is to create sort of a rough sketch of the cotter joint. And once you have a rough sketch of the cotter joint, you can actually start CADing in SolidWorks. And then you can create socket, you can create spigot, you can create cotter, and then you can assemble the cotter joint in the assembly mode. Okay, so I'm gonna start the design process. Before I begin, are there any questions? Okay, so step 1, design of raw dia. So what do I mean by raw dia? Raw diameter is nothing but this dimension. This dimension D. And it is the same dimension on the socket side is the same dimension on the spigot side. This rod diameter is designed in tensile failure. So tension or compression failure. And the equation is sigma t, because usually the tensile stress is lower than the compressive stress. The load that is applied P divided by pi by 4 d square. Sigma t will be given to us, value of P will be given to us, and from here we should be able to find out the diameter d. If you look at the failure area, the failure area is nothing but the circular cross section. Next step is design of Spigot Dia. So this Spigot Dia is nothing but this, and I'm gonna call this D1. Now I want to discuss the failure mode of this Spigot Dia, and for that let me draw a slightly larger figure. This spigot has a hole for quarter. So which means when the failure is going to happen, the failure will be something like this. And I want to show you the cross-section area where the failure has occurred. So this failure, if you were to look at the cross-sectional area where the failure has happened, this is the area where the failure has occurred. So let me give you the dimensions here. This is D1, but there is this thickness of the quarter. So this is T. So what we have is we have a failure area wherein you have the area of the circle, but you have to subtract the area of the hole. So what we need to do is we need to look at the equation, which is sigma t, which is the tensile failure of spigot, P divided by pi by 4 d1 square minus d1 multiplied by t. Now I need to write this down. T is the thickness of quarter. Now some of you may ask me, there are two unknowns, and that is absolutely correct, that in this equation there is d1 which is unknown and t that is also unknown. So what we need to do is we will need one more equation to solve this equation. So for that we go on to step 3. So step 3 is design of quarter thickness. And this quarter thickness, T, is determined because of the crushing in the spigot. So the quarter can crush in spigot. And I want you to understand how this crushing can potentially happen. So what we have is we have this spigot. We have the spigot, and then there is quarter, and then this quarter, which is going in here, can actually crush because of the loading. So just imagine that you are pulling it like this, and here you have socket, and I'm just going to show the socket as a dotted outline. You have the socket, and socket is being pulled over here, and there is a quarter that is holding these two pieces together. So as the socket is pulling on one side, the spigot is pulling on the other side. If you look at this cross-sectional area, the quarter could potentially get crushed. So this is the resisting area, or this is where the failure can take place. So sigma C is equal to P divided by D1 times T. Now, a word of caution. Many a times, the material for the quarter is different than the material for the spigot and socket. So you have to use the crushing strength of quarter material. And this is an important point, that sometimes we introduce something called as fail-safe design. So what happens in fail-safe design is you have a spigot, you have a socket, and you have a quarter. And all of a sudden, the torque or the power requirement or the torque requirement or the force requirement increases. And that force requirement could be way, way larger than this entire mechanical system can provide. So what you do is, in this entire mechanical system, there are three parts. Out of these, you deliberately allow one part to fail. And the easiest part that could potentially fail and can be replaced is quarter. So for example, you can allow quarter to either shear off or to crush, but then you realize that, hey, the quarter joint has failed. So you can actually take the quarter out, replace the quarter, and get the system functioning again. And if you look at the whole assembly, quarter is the cheapest element out of these three. You have socket, spigot, and quarter. So what you do is you deliberately allow quarter to fail. So you design the system in such a way that quarter is the weakest link. And based on the quarter material, what you do is you will find out. So from this equation, please note, from this equation, find D1 times T. D1 times T is P divided by sigma C. And D1 times T is known. Now, once D1 times T is known, you will go back. So please note, go back. And in this equation, substitute the value, substitute from step 3. And once you substitute the value of d1 times t, the only unknown here is d1. So you can find out the value of d1, and now you will have to go to step 3. So now what you need to do is use d1 from step 2 to find t. So if you look at this procedure, since the failure area is comprising of two unknown dimensions, one is d1 and the other dimension is t, what you will have to do is you will have to go a little bit back and forth in this design process so you can find out both these dimensions. So quickly, what you will do is to find out the Spigot dia and quarter thickness, you will substitute the value of P. This sigma T, and this is very important, this sigma T is the failure stress, or this is from the Spigot material, because sometimes the Spigot material and quarter material could be different. So this sigma T comes from the Spigot material, and what you do is you go to step 3, wherein you find out the value of product of d1 times t. Take that product, go to step 2, find out the value of d1, then come to step 3 and substitute the value of d1 and find the value of t. So, and this is very common in design. So many a times when you design, you start with a lot of unknowns. So sometimes what you have to do is you have to do either trial or error, or you have to go between different design steps to find out the dimensions. Everyone understood step 2 and step 3? Next thing is step 4. So in step 4, we want to find out the width of the quarter. Design of quarter width. Now let me show you how the quarter looks like. So if you were to look at the quarter, typically the quarter would look something like this. You will have a taper end, and then you will have a straight end. And usually if you look at the width is going to change. So the width of the quarter actually changes. So for design purposes, what we do is we look at the average width. So usually if you look at the quarter, we are going to look at the average width. And we are going to look at the shear failure. So this is quarter in double shear failure. And that is tau. This is again for quarter. This is for quarter. P divided by 2 times T times W. Please note that T is found out, is determined from step 3. So value of T is known. So what we will do is we'll substitute the value of P, we'll substitute the value of tau, which is the shear stress, and from here we should be able to find out the width of the quarter. And now this is sort of a conservative estimate, because if you think about it, some of you may ask me is, if you look at the way the actual joint is, this is the spigot end, this is sort of the spigot end, and this is sort of the socket end. So this is sort of the socket end. So you have socket on the right hand side, you have the spigot on the left hand side, and your failure, the shear failure, is occurring here and here. So these two widths are clearly different than W. But in the practical quarter joint, it is not possible to locate where the exact failure is going to happen, because you are going to hammer the quarter down. So even though you may have, say, you would say from the approximate proportion, my W would be a certain value. But in actual practice, because you are going to hammer and the quarter is going to deform, exact W cannot be found out. So as an approximate analysis, you will find out the average value of W, and that usually works out good for the design purposes. So in step 4, we are going to find out the quarter width. Now we are going to go to step 5. And in step 5, we are going to find out the design of spigot extension. Spigot extension. Now, to show you what spigot extension is, what I need to do is I need to draw a figure. So let me show you how it looks like. So this is spigot. This is spigot collar. And then look at the failure that has occurred over here. So this piece sort of came out. So the failure is over here. And why would this failure occur? Because please note, you have this quarter which is sitting over here, and this quarter actually pulls this guy out. So this is actually the shear failure on the side. So this is the shear failure. So we already know this dimension. This is nothing but D1. And I'm gonna call this distance L1. So tau, and this is for spigot, is equal to P divided by 2 times D1 times L1. Now please note, D1 is known from step 2, known from step 2. So the only unknown here is L1. And from here, value of L1 is known. Now, next step is we have to find out uh, the, the, the socket collar. So next step, so which is step 6, which is design of socket collar. And let's look at how this socket collar looks like. So this socket collar is going to look like something like this. And usually the failure of socket collar is because of the the crushing. So imagine that you have this cotter, and what happens is this cotter crushes against the socket collar. So this dimension is, I'm gonna call this as D4. And please note this dimension, it's same as the Spigot Dia, because Spigot is going to go inside this dimension. So this is Spigot. So this dimension, it's same as the Spigot dimension diameter here, which is D1, same dimension D1. So this failure is because of crushing. So this is crushing of collar by cotter, and that is sigma c is equal to P divided by D4 minus D1 multiplied by T. Please note, T is the thickness of the cotter. This is cotter thickness. That is known. D1 is the spigot diameter is known. The only unknown here is value of D4. And with this, we can find out the value of D4. Now, just to give you a view of the failure area, so check this out. This is where the failure is occurring. So this is D1. This is D4. And this is nothing but T. So D4 minus D1 multiplied by T is nothing but the cotter crushing the socket's collar. So with this, once we know the value of D4, next step, which is step 7, is determination of collar width or design of collar width. And if you look at the collar width, that is nothing but because of the double shear. So what I'm going to do is I'm going to show you how that failure takes place. And so let me show you here. So the failure is going to be somewhere here. And if you look at the way the parts that would come out will be one part here and the other part here. So this is the failure because of the shear. So, and if you look at the shear surfaces, and I will try to draw the faces over here, you're going to have one surface here, and you're going to have the other surface over here. Now, this dimension is D4. This dimension is D1. And this dimension is nothing but the L, I'm going to call this L4. So tau is equal to P. And please notice that shear is on the either side. So you will have D4 minus D1 multiplied by L4 times 2. Because please note, there is shear failure here and there is shear failure in the back. There is shear failure here and there is shear failure in the back. So in this, the value of D4 is known, value of D1 is known, the only unknown is L4, and with this you should be able to find out the value of L4. Next step is design of socket dia. And this socket diameter is actually studied or failed in pure tension. So this is pure tension failure. Now, if you look at the pure tension failure of socket, this is sort of difficult to visualize, but I want you to try to look at the socket and this socket has a hole for quarter. So what I want you to do is, I want you to visualize the cross-sectional area, which is over here. And the cross-sectional area over here is something like this. So this is the failure area. And this dimension, the most of the dimensions are known except for the diameter of the socket. And I'm gonna call the socket diameter, use a different color here. This is D3. This is D3. This is D1. This is T. So if you look at the area, sigma T is equal to P divided by pi by 4 D3 square minus D1 square. That gives you the total annular area minus, and I'm going to subtract the area which is shaded over here. This shaded area is nothing but D3 minus D1 times T. So this area is this shaded area. So you have this annular area, subtract the shaded area, and believe it or not, in this equation, D1 is known, D1 is known, T is known. The only unknown here is D3. So from this equation, you can find out what is the value of D3. The next step, which is step 9, is we have to find out the socket thickness. It's socket thickness. Now, socket thickness you can design based on the circumferential shear. So here is how the failure can happen. So you have the socket. And then from here, you can actually, the failure would be that this rod comes out of the socket. So rod coming out of the socket. So this dimension is considered as L3. This dimension is L3. And as you can see that initially the socket and the rod were connected, but under the loading, just the one end of the socket came out of the assembly. So the whole thing got pulled off. But this failure is the circumferential shear. Please note this dimension is same as the D. This dimension is same as the D, which is the rod dia. This is same as the rod dia. And tau is equal to P divided by pi times the rod dia times L3, wherein D is known and L3 can be found out. So with this, we should be able to find out the socket thickness. The next thing is step 10. Step 10 is spigot collar dimension. So spigot collar dia, design of spigot collar dia. And spigot collar dia, if you look at the way the spigot collar is designed, just to give you an idea where the spigot collar is. So this is where the spigot collar is. So this is the spigot collar. And if you look at the way the spigot collar is failing, this spigot collar failure is in crushing. So this is crushing failure. And this crushing failure is nothing but, I'm going to call this dimension D2. So let's, so if you consider this, this dimension is D2, and this crushing, this is the dimension D1. Please note this dimension is already known, D1. So which is P divided by pi by 4 D2 square minus D1 square is equal to sigma C. This is for spigot. D1 is known. So from here, you can find out what is the value of D2. Now, last couple of steps are we have to find out the spigot collar thickness. So we found the spigot collar diameter. Now we need to find out this spigot collar thickness. This dimension I'm going to call as L5. So spigot collar thickness spigot collar thickness. Now this is determined from circumferential shear. And so if you look at the way the failure can happen is you can just have this spigot collar staying where it is and the spigot separating out. So basically the spigot collar was here. And what happened that this collar, this is spigot collar, and this spigot got separated. And this thickness, I'm gonna call this L5, and tau is equal to P. This is for spigot, P divided by pi. And please note this dimension is D1. This dimension is also D1. D1 times L5. D1 is known. So from here, L5 can be found out. The last step is step 12. That is the bending of collar. So basically check cotter for bending. And this is sort of a slightly involved step. So I want you to pay attention very closely. So let's look at the whole assembly for a second. So what I'm going to do is I'm going to draw the whole assembly. So you have the spigot. This is the front view. Then you have the socket. And here we have a cotter. So this guy is the cotter. So this is socket. This is spigot. And this is cotter. Now I want you for a minute to visualize loading situation like this. So what's going to happen is the central part of the cotter will be pulled towards left. The top part of the cotter will be pulled towards right. So cotter, if you look at the way it's going to bend, it's sort of, and I'm going to show you an exaggerated way, it's going to bend something like this. This is the way the cotter is going to bend. Now please note that even though we want to design a fail-safe joint and we want cotter to be a weaker element, we don't want it to be too weak or to get stretched or to bend beyond its yield strength, because we don't want cotter to permanently deform. So what we need to do is we want to make sure that the cotter section is strong enough. And the way we do that is using the bending equation. So if you look at the loading on the cotter, and I'm going to show you the loading on the cotter. The loading on the cotter is something like you have uniformly distributed load at the center and you have the uniformly varying load at the end. So this is how the cotter is going to be loaded. So this is spigot side, this is socket side. So what happens is the spigot side is going to apply the load something like this. Socket side is going to apply the load something like this. And here is a reason why this loading distribution is assumed. Please note the cotter will not be loaded uniformly everywhere because of two reasons. First and foremost, cotter has a slight taper. And because of that taper, cotter is going to fit into spigot and socket, not in a very symmetric fashion, but what will happen is it will be hammered in and it will sort of be a press fit. And when something like that happens, you have the spigot, which is coming over here, which is kind of grabbing the cotter at the center. And because of that, as you know, since the cotter has deflected slightly in this orientation, the contact at the end will be minimum compared to the contact at the center. And the consequence of that is the loading is the way I have shown over here. However, one thing is certain, and I just tell you that based on the design that we have done, is this dimension is known. This dimension is D1. This dimension is also known. So this dimension is also known. We know the value of the load. We know P is equal to total load. So which means I can find out this is uniformly distributed load, uniformly distributed load and this is uniformly varying load. I can find out the magnitudes of uniformly distributed load and uniformly varying load, and I'm going to call this PUDL, and I'm going to call this PUVL. So these loads can be found out, and from these loads and the quarter geometry, we can find out the maximum bending moment. You can find out the BM max. And that maximum bending moment is derived based on this type of loading pattern. So I'm going to show you a horizontal quarter. And it's assumed that the quarter is supported over here, point A and point B. And basically, I would recommend that you can look at the equation for the maximum bending moment given in the textbook. And we are not going to look at the derivation of the maximum bending moment, but it can be derived based on what we need to do is first we have to find out the reactions, then we have to find out the bending moment because of the triangular load, bending moment because of the uniformly distributed load, and that gives you the equation for maximum bending moment. And from maximum bending moment, you can find out the loading or the stress in quarter. Please note this dimension is T, which is the thickness of the quarter, and this dimension is W. This dimension is W. So you can find out the BM max from the text equation, and this BM max divided by BD cube by 12, which is TW cube by 12, TW cube by 12. This is the moment of inertia of the quarter. That gives you value of sigma B, and that should be the sigma design of quarter. And many a times you will realize that this condition may or may not satisfy. And if the condition is not satisfied, then that is because we want quarter deliberately to be weaker when the loading on the quarter joint exceeds the design stress. So if, for an example, if the quarter joint is going to fail, what we want quarter to fail in bending. So here is something important. And we want quarter to fail in bending so that the system is safe. And this is the principle of fail-safe design. So because it's much easier to replace the quarter than replace the socket and spigot. So this is how the quarter joint is designed. So there are systematic steps, and if you look at the textbook follows the exact same steps, but there are some additional dimensions that you want to find out based on the empirical relationship, and you can look at those dimensions from the textbook, and then you can follow this recipe, step-by-step recipe, and you should be able to design the quarter joint. That is what is asked in quiz 1, and I'm gonna stop here today. And if you have any questions, I would be happy to answer. So L3, so for L, okay, L3 is this dimension, this. So imagine that a rod end is inside the socket, but what happened was that rod got pulled out of socket. So that is the L3 dimension. Yes, I will go back to D1. Now D1 is in step 2, and please understand this is a classic design step where the number of unknowns are greater at step 1, I mean step 2. Step 1 is finding out the rod dimension. D1 is the spigot diameter. If you look at the failure of the spigot diameter, there is a hole in the spigot. That is because we want cotter to be placed in that hole. So if you look at the failure area, you have the circular area minus the rectangular section. So you have the circular area, and when I say circular area, I want you to look at this figure. It is the circular area minus the rectangular area, and the shaded area is where the failure is taking place. So look at this area. This is the failure area, which is the area of the circle minus area of the rectangle. So, but unfortunately, the rectangle is d1 multiplied by t. So t is not known. So what we need to do is we need to go to next step, which is step 3, where we find out the value of t based on the crushing of the cotter. And what we do is we find the value of t, take that, substitute it back in equation or step 2, and get the value of d1. Once we know the value of d1, we go back to step 3 and find out the value of t. Next question. So whenever you look at design, you will never find a cotter joint that is designed exactly as per your spec. So for an example, if your rod dimension is 38.2, you will never find a rod or a cotter joint that will have 38.2 as the rod diameter. You may have the rod diameter as 33, 34. So you should always round it to the higher side. So don't keep the dimension in fraction, because it never happens in design. In design, what you want to do is the dimensions that you calculate from these calculations are sort of a guideline. You want your dimensions to be greater than these dimensions, and those greater dimensions should be the standard dimensions. So in the design, what you're going to do is when you go to industry, you will determine all these dimensions, and then you look at the catalog, and then you pick up the catalog item that satisfies these design criteria and dimensions. So whenever you find a dimension, please round it off to the higher side. Even better, if you want to actually look at a cotter joint that is readily available at McMaster or Granger, they will give you standard proportions of cotter joint. So you can use those, but make sure that the dimensions of that cotter joint are greater than the dimensions that you found out using the calculations, engineering calculations here. Okay, any other question? if there are no questions, please start working out the problem. And I just want to tell you, there are a couple of worked out problems in the book. Yes, I recommend rounding between the calculations. That finally means that your quarter joint will be slightly bigger, but clearly it would be safer. And if you look at the website, the canvas, I have actually uploaded some worked out problems on quarter joint as well. So you can use those as reference. And if you look at the past video lecture, there I have solved a quarter joint and I found the actual dimensions. You can use that as a reference too. Are there any other questions? If you have questions, please raise your hand, or you can type it in the chat window. Or class is dismissed. Thank you very much, and I will see you next class. And have a good rest of your week. If you have any questions, you're welcome to send me an email, and then I would be happy to help you. Please look at the calculations given in the textbook and the worked out problems on Canvas. So for homework 1, it does not, because it's just mechanics of material. They are not really a design problem. But from homework 2 onwards, I would recommend rounding off. But for homework 1, I wouldn't worry about it, because homework 1 is just to give you some practice on the mechanics of material. But from homework 2, when you will be solving actual design problems, start rounding. Okay, I will upload the video and I will upload the slides onto Canvas. Thank you very much and have a good night.